Fractals by Roglan. The discovery of fractals begins in the 17th century with observing patterns of recursive self-symmetry. This is the idea that random sets as an image has been rescaled from an independent copy or subimage. It is decomposed as a union. So basically you could zoom in on an image, take a piece of it and scale it up, and you would have the same image. A mathematician by the name of Felix Haseldorff first introduced the idea of fractals in 1918. Fractals come from the Latin root word fractus, which means irregular or fragmented. Mandelbrot in 1975 confirmed the development of the idea by giving the mathematical phenomenon the title of fractal. The first key detail needed to understand fractals is recursive self-symmetry. This is the process when you can break a piece of a fractal and amplify it and get the same result. There are three types. Exact self-symmetry, when the sample is broken and zoomed in and is exactly the same. Quasi-self-symmetry, when it is approximately the same when you zoom in. And statistical self-symmetry was when the proportions are scaled to about the same. This means that they are not identical, but they hold a similar shape. This one also has the most real-world applications. So now the biggest question is, what is the actual definition of a fractal? A fractal is a paradox expressed by repeating patterns or an equation that keeps getting more and more complex. All fractals show a degree of self-similarity, meaning that they're copies of themselves, and fractals are never-ending loop that are driven by feedback. They can exist on the 1D, 2D, and 3-dimensional plane. The image on the right shows a plant cell undergoing cell division. To continue our definition with fractals, fractals are also defined as complex geometric shapes. The sides of fractals are pieces of infinite segments with angles between them. Typically the number is between 1 or 2 when you use the equation, which will be later described. Fractal dimensions are also a way to measure the fractal's complexity. And topographical dimensions is the roadmap of what the object looks like. Fractals are 2D objects in their topographical sense, however, their areas have those of higher dimensions. The key takeaways from those first few slides were that all fractals are recursive, meaning that they're repeating patterns of themselves, and fractal dimensions are accurate descriptions of their complexity and are considered the complex figures, so basically how many curves and twists they have. Different shapes / types of fractals. That means that the more you look at fractals, the more copies of the same picture you see. An example of this is a fern, which looks very similar to what you're looking at right now. The most famous fractals are the circular triangle, the merged sponge, and those fractals beginning with the solid shape and the equation repeatedly subtracting to make a fractal. The key takeaway though is that fractal dimensions are greater than the topological dimensions to make a fractal. The chaos theory is one of the more complex ideas in fractals. Chaos is defined as full disorder. The basics of the theory attempts to explain that when there's 2 or more dependent variables, the event becomes more unpredictable due to small change. Fractals, in simple terms, are visuals of chaos. Continuing on with the chaos theory and to more of its implications on fractals, there are infinite variations to change the initial equation. These infinite changes of the variables can make it so that infinite fractals can occur. The main relationships to take away from the chaos theory, though, is that the chaos theory states that the future is dependent on the past state changes. The formula is that x of 1 is equal to x times 1 minus x, where x of 1 is the future state and x is the past. The basic equation of the fractal is d is equal to the log of n over log of s. N is equal to the number of parts the fractal has. S is equal to the new part while being compared to the original, and D is equal to the overall dimension of the fractal. Some of the more generic application of fractals are just architecture in general, along with African art and Indonesian art. And another more specific fractal that got applied recently was that Nathan Cohen created a compact radio antenna. He used a meager sponge fractal to maximize the reaching power of the antenna with the least amount of space. The most common medical application of this would be detecting cancer cells. It is key when detecting cancer cells due to their unpredictable and rapid cell division. When analyzing cell movement, the division creates creates a fractal. The normal cells would divide sequentially, and this would create a lower fractal number. The most common geographic application is the coastline paradox. This is when you measure the coast with a more specific tool, you always end up with a larger value.